Hi there, I'm Reshma Abraham and welcome to my channel Deep Dive. Today I'll be walking you through text to photorealistic image synthesis using stacked GANs or stacked generative adversarial networks. Now this is a 2017 paper and it proposes a stacked GAN structure that takes in text descriptions as input and provides high-resolution photorealistic images as output. Now think of this method as a painter with an idea. When the painter wants to convert his idea into a painting, he would first throw in all the base colors, maybe roughly sketch all the objects that would be present, and then it is only in the subsequent stages that he would add in more compelling details, refine the painting, or correct any mistakes that are present in the painting. This is exactly what a two-stage stacked GAN proposed in the paper does. Take a look. Okay, so this image will help you understand the idea behind the paper. So as you can see, the stage 1 GAN architecture will generate low resolution images. And what it does is it basically sketches only the primitive shape as well as the color of the object based on the text description that is fed into the block, right? Now your stage 2 is where all the fun part begins, because your stage 2 will take the stage 1 images as well as the text description and generate a more high resolution image, as you can see here. So what happens in stage 2 is a sketch refinement process. That is, your stage 2 is able to rectify any defects that are present in the stage 1 low resolution image. At the same time, add more compelling details or more photorealistic details to it based on the text description. You might be wondering if this is the first time a paper is proposing text to image synthesis. Absolutely not. Then how is this paper different from its predecessors? Well, the contribution of this paper is threefold. Firstly, this is the first time a paper is proposing a stacked GAN model that is capable of generating 256 by 256 high resolution photorealistic images from text descriptions. Secondly, this paper proposes a new conditioning augmentation technique for conditional GAN training so that it stabilizes the training and also increases the diversity in generated samples. Thirdly, this paper also comes with qualitative and quantitative evaluation results of this method on 3 data sets. Now, what is conditioning augmentation technique and why was it introduced? Let me explain. Now, we know that the input to our system are text descriptions, right? Now, these text descriptions cannot be directly fed into a generator model. So, we first encode these text descriptions into text embeddings, which are nothing but fixed length vectors. Now, these text embeddings are then non-linearly transformed into latent space variables. Now, the dimensionality of these latent space variables are very high, greater than 100. And that is not decidable, especially when we have limited image text pairs for training. It is going to cause discontinuity in training for a generator. This is where conditioning augmentation technique comes in. So what does conditioning augmentation do? Well, conditioning augmentation technique randomly samples the latent variables from an independent Gaussian distribution. Now the mean and diagonal covariance metrics of this distribution are a function of text embeddings. Now remember, text embeddings are the encoded version of our text description input. Now the benefits of conditioning augmentation technique are twofold. Firstly, it yields more training pairs given a small number of image text pairs. Now this in turn encourages robustness to small perturbations. This simply means that because more data is available or training data is available, our model is capable of neglecting small variations or insignificant changes in the data. Secondly, this technique introduces randomness, and that is beneficial for modeling text-to-image translation because in some cases the same sentence can correspond to objects with various poses and appearance. So now let's move on to the next section, which is architecture. This is the architecture that is provided in the proposed StackGAN method. Now in this image, the first half represents your stage 1 GAN architecture, and the bottom half it represents a stage 2 GAN architecture. What we'll do is we'll break this image into two halves and take a look at each stage separately. So this is our stage 1 GAN architecture. Now what you see here is your stage 1 generator block, and this is your stage 1 discriminator block. Now the input to a generator has to be a vector, right? So what is done is a text description is encoded into text embeddings. Now text embeddings are nothing but fixed length vectors. Now this text embedding is then fed into a conditioning augmentation block, right, to generate C0 sharp, which is a conditioning vector. Right. Now this conditioning augmentation block is a fully connected layer which generates mu naught and sigma naught, which are the mean and standard deviation of a Gaussian distribution from which your latent variables or your conditioning vector is randomly sampled. Now this C0 sharp or your conditioning vector is a ng dimensional vector. Alright, so this ng dimensional vector is concatenated with a noise vector of dimension nz, right, and the resultant vector is then fed to a series of upsampling blocks that are present in your generator, and this will generate a resultant image of resolution W0 by H0. And in our architecture diagram, this W0 and H0 is 64. That is why you have a 64 by 64 resultant image, right? Moving on to the discriminator. Now in the discriminator end, we have two processes happening. Firstly, the output of our generator along with the real set of real images are fed to a series of downsampling blocks present in the discriminator, and this generates an image filter map of dimension MD by MD, right, and from our diagram we know MD is 4 here, so it's a 4 by 4 image filter map that is generated. Now meanwhile, our text embedding is also fed to the system or to the process, right? What happens is your text embedding is first compressed using a fully connected layer. It is compressed to ND dimensions, right, and then it's spatially replicated to create a text tensor. Now this text tensor is then concatenated with our image filter map which is generated earlier, and these two together is fed to a 1 by 1 convolution layer. Now it is this convolution layer that learns all the features from both our image filter as well as our text tensor. Now as you can see, the convolution layer has only one node, and this node will generate our decision score. So the output from your discriminator is the decision score, which will be either 0 or 1 depending on whether the image is classified as real or fake. So that is all about our stage 1 GAN. Let's move on to the second stage. This is our stage 2 GAN architecture. So as we know, the stage 2 GAN input comprises of our text descriptions as well as low resolution images that are generated by the stage 1. So the text description is encoded with the same text encoder to generate text embeddings. Now these text embeddings are passed into the conditioning augmentation block. Now a point to be noted here is that the stage 1 and stage 2 conditioning augmentation comprises of different fully connected layers. So as a result, the mean and the standard deviation that is generated by each of these blocks are different. So naturally the latent variable or our conditioning vector will also be different, right? So here the conditioning vector is represented by C sharp. Now the C sharp is spatially replicated to generate a text tensor of size mg by mg by ng. Alright. So now let's take a look at the low resolution image. The low resolution image is fed into a series of downsampling blocks. Now these are downsampled till its size reduces to mg by mg. Alright, so after which the image features are concatenated with the text descriptions or the text tensor. And the text tensor, the coupled features are fed into the residual blocks. Now, residual blocks are designed in such a way that they learn the multimodal representation from the text and image features. You might wonder what are multimodal representations. So let's see. When images are fed to a model, they are represented as pixels. When text is fed to a model, they are represented as vectors or vector counts. In our case, we have both image and text, right? So we need a joint representation to represent both these modalities. And that is what is achieved in these residual blocks. The output of the residual blocks are further passed through a series of upsampling blocks till the size of your output image increases to W by H. In our case, 256 by 256. And thus the generator generates high resolution images. Moving on to the discriminator. The discriminator is quite similar to the one that is present in our stage 1, except that here you have one extra downsampling block, and that is mainly because your input size is really high. It is 256. Earlier it was 64. So hence we have one extra downsampling layer. So that is all about the stage 2 GAN architecture. Let's move a little further and take a look at the training. During training, the discriminator is fed with both positive and negative samples. Positive samples are real images with their corresponding text descriptions. But the negative samples are of two groups. The first group contains real images with mismatched or wrong text embeddings, and the second group contains synthetic or fake images with corresponding text embeddings. Let's understand the training process. Training happens in two stages. In the first stage, we iteratively train the discriminator and the generator of stage 1 GAN for 600 epochs by fixing stage 2 GAN. And in the next stage, we iteratively train the generator and discriminator of stage 2 GAN for another 600 epochs by fixing stage 1 GAN. Now the optimizer used here is ADAM, and the training is performed for a batch size of 64 with an initial learning rate of 2 into 10 raised to minus 4. The learning rate decays to half its previous value every 100 epochs. To validate their method, they used extensive qualitative and quantitative evaluations and experiments on the proposed method. For this, they used the Cub birds dataset, the Oxford 102 flowers dataset, and MS Cocoa dataset to show the generalization capability of their method. For quantitative evaluation, our authors, they used the inception score, which is computed as follows. Here X denotes one generated sample and Y is the label predicted by the inception model. D subscript KL stands for the KL divergence between your marginal distribution and the conditional distribution. Now the idea behind using inception score is if the score is very high, it means that the samples are very diverse, at the same time meaningful or realistic, right? For this, the KL divergence between the two distributions has to be very large. Now I'm not going into detail about the KL divergence in this video because it's out of scope. So let's move on. Now to ensure the visual quality of the samples, our authors, they also conducted human evaluation. So what happens is various human users, they were asked to rank the results by the different methods. Okay, then the average rank of these results were computed to evaluate the performance of the methods. Alright, so that's all about the quantitative and qualitative evaluation. Let's take a look at the results that were generated. What you see here is a table with the inception score and the average human rank that is computed for our StackGAN as well as two other state-of-the-art text-to-image synthesis methods on 3 datasets, that is Cub, Oxford and Cocoa. Now there are 2 key points that you need to note from this table. Firstly, compared to the first method, the proposed StackGAN achieves almost a 28% improvement in the inception score on the Cub dataset, that is from 2.88 to 3.70, and a 20% improvement in the Oxford dataset that is from 2.66 to 3.20. Secondly, if we look at the second half of the table, which denotes the human rank, we see that the StackGAN is able to achieve far better average human rank compared to the other two methods. Now, this indicates that the StackGAN is capable of generating more realistic samples that are conditioned on the text description. So in a nutshell, what you need to understand is that the proposed StackGAN is capable of generating the best inception score as well as average human rank compared to the other two methods on all the three data sets. Next, we'll take a look at component analysis, where we'll analyze the different components of our proposed StackGAN model on the CUP dataset with other baseline models. Personally, I feel this section is very important to understand why they decided this architecture and how the various components of this architecture influences the final inception score. The first four rows of this table denotes the performance of the method with a stage 1 GAN architecture alone. If a stage 1 GAN architecture is used to directly generate a 64 by 64 resolution image, we see that the inception score is 2.66, which is fairly low. Upon increasing the architecture output resolution to 256 by 256, we see that the inception score further reduces to 2.48. Now this denotes that the stage 1 architecture alone is incapable of generating any plausible samples. Now if we add conditioning augmentation to both these architectures, we see that the inception score slightly increases to 2.95 and 3.02, but this increase is not significant, mainly because though it adds diversity in your output samples, the generated samples are not as realistic as expected. That is, they lack photorealistic details. This demonstrates the necessity of the proposed stacked structure. We see that a 128 by 128 StackGAN architecture without conditioning augmentation itself is generating an inception score of 3.20. However, the best performance is shown by the high resolution StackGAN with conditioning augmentation and text-wise. It is capable of generating an inception score of 3.70. By text-wise, we mean that the input text description is fed to both the stages of the StackGAN. So that's all about our StackGAN paper. Hope this video was helpful. If it was, do like and subscribe to the channel and let me know your thoughts in the comment section. I'll be reading them. I'll add the link to the code as well as the paper in the description box. Check them out. So thank you so much for watching, and until next time, take care and goodbye.